Hi everybody, the purpose of this video is to go over the very last section in Chapter 1. Yep, I'm talking Section 8. And here we are going to talk about absolute value equations and inequalities. We are going to go over a few basic concepts. We are going to then talk about absolute value equations and how to solve them, and also how to solve the two types of absolute value inequalities. We will go over some special cases, which in most cases makes your life a lot easier. They were going to apply the concept of the absolute value to the concept of distance and tolerance measurement. I guess I should have spelled that a little bit better in my when I prepared the slides. The absolute value of a number, say alpha, gives the distance from that number to 0 on the real line. Okay, so take a look at the equation, the absolute value of x is equal to 4. The solution to that equation are all those values of x whose distance from 0 to that particular value is equal to 4. So notice the distance from the origin to this particular point, which by the way is negative 4, well, that distance is 4. The distance from 0 to this particular point, which by the way is positive 4, that's also equal to 4. Therefore, the two solutions that makes this equation true are the numbers negative 4 and 4, and that is our solution set. And that's pretty much the way that we look at absolute values. Okay, now in looking at absolute values or inequalities, we actually have three different cases. The first case is when the absolute value of x is equal to k. In that particular case, we have two solutions, and they are points. They are going to be the point k and the point negative k. There they are on the real line, and that would be your solution set. The second case is where we have the absolute value of x is strictly less than k, or is less than or equal to k. In this particular case, our solution is going to be an interval, but it's going to be a bounded interval. It will either be bounded between negative k and k, not including k's, which in this particular case means we have an open interval, or it's going to be bounded between negative k and k, including both negative k and k. In this particular case, we actually have a closed interval. And then the last case is when the equality is greater than or equal to. In this case, the equivalent solutions would be x less than negative k, or x is greater than negative k, or the non-strict equivalent. In that particular case, your solutions will be a union of two disjoint intervals. In this particular case, will be for the union of the interval from negative k at negative infinity to negative k, union with the interval from k to infinity. So those are the three cases that we have. You also find a certain special case where we have where the absolute value of one expression might be equal to the absolute value of the other expression, and that can be resolved by first considering a is equal to b, and then a is equal to negative b. So this is our first case. This right here is a case 1 problem. So how do we solve that? Well, this results in two equations. The first equation is going to be 5 minus 3x is equal to 12. The other equation is going to be 5 minus 3x is equal to negative 12, because once again, this is a case 1 problem. Okay, so we have to solve these two equations. To solve the first one, we can subtract 5 from both sides. If we do, we will have negative 3x is equal to 7. Divide both sides by negative 3. And we have that x is equal to negative 7/3. 7/3. Once again, over here, we can subtract 5 from both sides. Of course, in this case, the 5's cancel. We still have negative 3x, but now we have negative 17. Divide both sides by negative 3. And we have that x is equal, that should be a negative there, 17/3. And therefore our solution set will be these 2 points. It will be negative 7/3, comma, 17/3. Okay, those are my kind of problems. Here's our next example. Now, this example in its current form, we cannot determine which case it is, because we cannot determine the case until we have the absolute value, some expression, is less than some number or greater than some number. Okay, so before we can make a determination, we actually have to add 1 to both sides. So let's go ahead and do that. Plus 1, and then we will have that the absolute value of 2x plus 1 is strictly less than 7. Notice this is a case 2 problem. So the equivalent expression, that should be 7, is going to be a compound interval, which is -7 is less than 2x plus 1, which is less than +7. So we want to solve this compound inequality. And of course, the way we do this is by isolating x in the middle, and therefore we want to subtract 1 from all 3 sides. And if we do here, with these ones will cancel, we will have -8x, no, -8, which is strictly less than 2x, which is strictly less than 6. Now we can divide all 3 sides by 2. And we will have -4 is less than x, because these cancel, which is less than 3. Okay, now, and therefore our solution in interval notation is going to be the open interval from -4 to 3. Once again, keep in mind when you write your answers in interval notation, make sure you put the smaller number first and the larger number next. For this example, we cannot determine the case until we have actually isolated the absolute value expression. So to do that, we want to add 1 to both sides. And then we will have the absolute value of 2 minus 7x. These will cancel, is strictly greater than 5. Now this is a case 3 problem. So to solve this, we need to solve the following 2 inequalities. The first one is 2 minus 7x is strictly less than -5, and 2 minus 7x is strictly greater than 5. Those are the 2 inequalities. Okay, so let's go ahead and do that. The first thing we want to do is subtract 2 from both sides. So -2 here, -2 here, working on this one. These cancel. We will have -7x is strictly less than -7. Okay, so now we are going to divide both sides by -7. Since I am dividing by a negative number, I need to flip the direction of the inequality. So now it's going to be positive. These will cancel. I am left with x, and then -7 divided by 7 is 1, so I'm going to have x is greater than 1. Let's go over here. Once again, I want to subtract 2 from both sides. -2, -2. The 2's cancel. I will have -7x is greater than 3. Once again, I have to divide both sides by -7 to get rid of the coefficient. Since I am dividing by a negative number, I need to change the direction of the inequality. These will cancel. I am left with x, and then over here I have -3/7. So I have x is less than 3/7 as one of the solutions. That is in interval notation, that is from -infinity to -3/7, not including -3/7. And then over here I have x is greater than 1. That's going to be the interval from 1 all the way up to infinity. Once again, I am not including 1. Now both of these intervals solves this equation. So I need to union them, because it's either this one or that one, and that implies a union. And this would be a solution to this particular problem. Well, actually, not a solution, the solution. Okay, so let's talk about a couple of special cases. And here's one. Here we have 2x minus 5 is greater than or equal to 7. Now notice this right here is an absolute value. This term right here will always be greater than or equal to 0. Okay? So over here we have some number which is going to be positive with always non-negative. Always non-negative. Being greater than or equal to a negative number. This is true for any value of x. For any value of x, you're going to have something which is either 0 or greater. And that will always be greater than a negative number. So as a consequence, the solution set is the entire real line. How do you write that in interval notation? It is the open interval from negative infinity to infinity. Now over here, I forgot I actually had that stuff in here. Well, notice here, I actually have a number here that is always going to be positive. Okay? No matter what we do, this will be greater than 0. As a consequence, this will always be greater than negative 3. There's no way 4x minus 7 could ever be less than negative 3 because the smallest value this thing can take is 0. And therefore, there is no solution to this particular equation. As a consequence, the solution set is the empty set, which we've kind of mentioned down here. Okay, and then finally we have this one. This is a case 1 problem. So we have basically two possible solutions. So the first one is 5x plus 15 is equal to 0. The other one is 5x plus 15 is equal to negative 0. Well, that pretty much is just this one, so this one doesn't particularly matter. Okay, so we just go ahead and solve this one. Can be rewritten as 5x is equal to negative 15. Divide both sides by 5. You will have x is equal to negative 3, and that would be our solution. So our solution set would just simply be negative 3. And that's pretty much all that we're talking about here. Now, the next set of examples is where we can actually use the absolute value to describe the distance between two quantities. So here we want to find, here we have the statement. The statement says that the distance between P and Q is equal to 11. And as I remember, that as I recall, the absolute value of a particular number x, or all those equal to 4, is basically all those values where the all those values where the distance from x to the origin is equal to 4. So here we want to find the distance between these two values being equal to 11. And the way we can write that is that the distance between these two quantities, Q minus P, that the distance between these two quantities or the distance between the difference of these quantities, there it is, we want that to be equal to 11, and that is how you would write that equation. The distance between the distance between x and the origin is 4. The distance between the difference of these two and the origin, which would basically be P minus Q, is going to be equal to, I forgot the other term there, 11, and that's how we would write that. Now for this one, we need to understand that within implies a strict inequality, strictly less than. So here we want to determine that the distance between n and 6 is less than 0.001. This is actually basically a tolerance assessment. So the way that we write that equation is, once again, the distance between n and 6, we want that to be less than 0.01. If we were actually making a disk, we could say that we want the diameter of the disk to be 1/100th of an inch within 6 inches. So it's basically a tolerance measurement, which we tend to use in engineering all the time. Okay, now this one we say we have T is no more than 9 units from 8. Now no more. So within is strictly less than. This is a non-strict less than. So what we're saying is that we want the distance from T to 8 to be less than or equal to 9. So that would be T minus 8, distance from T to 8. We want that to be less than or equal to 9. And that's how you would write that. And I have one more. and this is no less. So if no more is a non-strict less than, then no less is a non-strict greater than. And here you have the distance between R and S. I'm sorry, between R and 26. We want the distance between R and 26. It's R minus 26. We want that to be less than or equal, greater than or equal to 7. So that's how we write that, and that's how we actually interpret these particular words, which will come in handy when you do your homework for this section. Okay, so this right here is an example, an application which you might encounter which you will encounter in your homework. Here we have in quality control and other applications, we wish to keep the difference between two quantities to within some predetermined amount. We call this the tolerance. We do this all the time in engineering drawings and whatnot. So suppose that we have this relationship, y is equal to 2x plus 1, and we want y to be within 0.01 unit of 4. For what values of x will this be true? Well, remember, within implies less than. So we want the distance between y and 4, y minus 4, to be strictly less than 0.01. But however, this is y. So we can actually use this to figure out what the equivalent x should be. Well, that basically means that, so if that's the case, then we can substitute this in for y, and we will have that 2x plus 1 minus 4 needs to be, the absolute value of that must be strictly less than 0.01. We can simplify this, and we will have that the absolute value of 2x minus 3 is strictly less than 0.01. And this will be a case 3 problem. Okay, so that basically, this will be a case 2 problem. And that implies the compound inequality of negative 0.01 is less than 2x minus 3, which is less than 0.01. And this is what we want to solve. Now, the very first thing that we can do is add 3 to all three sides. Plus 3, plus 3, plus 3. And if we add vertically, we will have 2.99 is strictly less than 2x, which is strictly less than 3.01. Now we can divide all three sides by 2. And if we do, we will have 1.495 is strictly less than x, which will strictly be less than 1.505. So that basically means that x must be within the range of 1.495, comma 1.505, this particular open interval, for that y to be within 0.01 of 4. We have a few problems left to do, and here is the next one. This one here, we have an absolute value equation which is quadratic. Now notice that this is case 1. Therefore, we are going to have two equations. The first one is x squared plus 11x plus 29 is equal to negative 1, and the other one is x squared plus 11x plus 29 is equal to positive 1. Okay, well, putting this one into standard form, we'll add 1 to both sides. That will give me x squared plus 11x plus 30 is equal to 0. And this one will give me x squared plus 11x plus 28 is equal to 0. Okay, well, both of these factor. This one actually factors into x plus 5 times x plus 6 is equal to 0, and the solutions will be x is equal to minus 5 or x is equal to minus 6. This one factors into x plus 7 times x plus 4 equals 0, and this produces solutions x is equal to negative 7, x is equal to negative 4. So our solution set would be negative 4, yeah, you guessed it, negative 5, negative 6, negative 7. And I believe the 1 or 2 that you have in your homework comes out just about that neatly. I'm not exactly sure, but I'm pretty sure it does. And then finally, for our last example, we have an absolute value rational inequality. Okay, this one looks pretty intense, doesn't it? Well, let's check this out. Here we have the absolute value of x minus 4 over 5x plus 1 is greater than or equal to 0. Now, what do we know about absolute values? Well, this right here is always greater than or equal to 0. Therefore, the entire real line satisfies this particular equation. Or does it? Remember, we need to exclude every value of x that causes this expression to be undefined. So what you need to do is to find those values, or in this particular case, that value of x which causes this denominator to go to 0, because when this denominator equals 0, this term is undefined, and therefore the inequality is undefined. So we need to find that value of x which causes 5x plus 1 to be equal to 0. And what value is that? Well, that will be x is equal to negative 1/5. So we need to exclude this particular point. And how does that affect our solution? Well, our solution will be basically all values on all points on the real line except that point. And how do you write that in interval notation? Well, that is going to be the interval from negative infinity all the way up to negative 1/5, not including negative 1/5, unioned with the open interval from negative 1/5. I almost forgot the negative sign there, all the way up to infinity. And that is the interval notation representation for every single point on the real line except that point. And that, of course, would be our solution set. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.